Residuals. Alright, so for this presentation we're going to construct and interpret residual plots. We're going to address how accurate our least squared regression line is. We're going to describe how slope, y-intercept, standard deviation of residuals, and R-squared are all influenced by outliers. So let's get started. First, what is a residual? So when you plot a line, it will almost never pass exactly through all the points that you have on your scatter plot, right? We saw that on the other presentation. A residual, I mentioned it, a residual is the difference between an observed value of the response variable and the predicted value of the regression line. Basically, it's the dot minus the line. Or in other words, the y minus the y hat. Remember, the y represents the actual dot, the actual value, and y hat represents the predicted value. So it's the dot minus the line, y minus y hat. And keep in mind that a good residual line is going to try to make these values as small as possible. A residual plot is a secondary scatter plot that you make representing the residual difference between the dot and the line. If you can imagine, basically it takes the regression line and flattens it out horizontally and then graphs the dots on top of that line again. Based on their vertical axis, right? So it zeroes out, it makes the line that you graph, the least squared regression line, the x-axis, and then it plots each one of these points on top of that chart vertically, so you can see just how far away each of the dots are from the line. It basically just graphs the distance away from the line each plot is, right? Now, in residual plots, randomness is good. We want it to appear as if these are randomly scattered about the plot. The reason for that is because if it wasn't random, then that would suggest that there is a pattern that we missed, right? So for example, if I had a residual plot that showed dots starting out below, then going above, and then going back down below my line, then that would suggest I have a scatter plot where I've got dots that start out below my residual line, go above, and then come back below. This is not a linear scatter plot. So remember, we've talked about how R and R represents specifically linear representations, right? This is a least squared regression line that is graphed linearly. This pattern is not a linear pattern. These scatter plots, this data, does not follow a linear pattern. So if you have a pattern on the residual plot of any kind, maybe a U-shape or the other direction a U-shape, or maybe it waves up and down sinusoidally, perhaps, like a sine function or a wave function, then that tells you that you're graphing a line to represent something that shouldn't be graphed with a line. And you probably need to stop right there. And maybe graph it a different way. Maybe try a different type of regression, which we'll get to later on, right? But in any case, if you see a pattern on your residual plot, an obvious pattern, then you should check your data and maybe reconsider whether or not this data is best represented with a linear regression line. Here's why that's important. An example AP problem would ask, is a linear model appropriate for this data? A lot of times on regression problems, they'll throw this in there. Is this model appropriate? You can answer this one of two ways. Option one, if there's no obvious pattern left over in the residual plot, then the linear model is appropriate, or whatever model that you pick. If this is a linear model, then yes. Try a exponential regression, then you can put option two. Because there is an obvious pattern, the linear model is not appropriate. Those are the only two ways you need to try to answer that question. Either there's no pattern, so it is, or there is a pattern, so it's not. That's it. 3 points on the AP test right there. Next up, we have standard deviation. So the standard deviation in regression is the standard deviation of the residuals, right? It's not something that's talked about very commonly. It's not something that you calculate by hand normally. And the reason for that is this. Basically, you take each y value, or each y value for each dot on your scatter plot, and you subtract the y value for the line. You square that, you add them all up, you divide by however many points you have minus 2 this time, and then you take the square root. If you have many dots on this scatter plot, then that would be a very tedious process. So most of the time it's either going to be given to you or you can find it in Word, right? This value, what it tells you is the approximate size of a typical prediction error, right? I think a lot of times they'll even refer to it as a standard error, even though it means something different, but whatever. But the standard deviation in this case tells you how far off your line is going to be from your actual scatter plot on average, right? Typically, how far away your line is going to be from each individual dot. And keeping in mind, the point of the least squared regression line is to make that distance, make that value as small as possible. So a good line is going to try to minimize the standard deviation as best as it can. Of course, if it's a perfect line, then your standard deviation will be 0, but that's not realistic, so we don't expect that. Here's why that's important. An example AP problem for this. Interpret the value S equals blank. S in this case represents the standard deviation for the residuals. So the way you would answer that question is, when using the least squared regression line with X equals whatever your X was and Y equals whatever your Y was, we will typically be off by about blank S units. So here in this blank you would just put whatever your X is, just put whatever your Y was. In this blank you would put whatever your standard deviation was, and then of course your units for Y, because it is a calculation based on the residuals, which are a Y value. Alright, coefficient of determination, or R squared. This is one that's very common. I think on the video where I showed the 2-variable summary statistics on the calculator, R squared was one of the first ones we saw, right? It gave us A, it gave us B, and then it gave us R squared right away. This one is very common. Basically, it's the fraction of the variation in values of Y that are accounted for by the least squared regression line. And you find it very similarly to the way you find standard deviation. Again, this is not something you will normally do by hand. The only way you would do it by hand is you would square the R, because they are the same R, as long as it's linear anyway. So R squared, what it really tells us though, is how much better the least squared regression line does at predicting the values of Y than simply guessing the mean for each Y value, right? So it basically accounts for how much of the variation is due to the actual data and not from some other source, right? So example, interpret the R squared value, R squared equals blank, right? So the way you would answer this is about, and then you would put your R squared written as a percentage. It'll usually be given to you as a decimal, so you have to move the decimal over or multiply by 100 or however you want to think about it. So about R squared percent of the variation in Y can be accounted for by X. Basically, it says how much of the variation in Y is because of X. What percent of the reason Y is changing is because X is changing. And it's an interesting thing to conceptualize, right? It basically tells us what impact the X actually has on the Y, right? One of the reasons we do this is to figure out if there is a relationship between some X variable and some Y variable. This tells us how much of that variation is because of X, right? So it tells us, well, how strong is that correlation? If it's a very high number, then of course that, oh, well, that's very good. That means that there is obviously a relationship. So this is, you know, conceptually it's a nice thing to think about, and mathematically it's very easy to calculate because it'll either be given to you or you find R in the calculator and you just square it. All right, so some things you should know about. I find these things outdated, but a lot of AP questions still are formatted this way. So they'll give you what they call computer regression output. I don't know what computer they're using, but it is a very old computer to give regression output. So basically they'll give you output data. It'll have a mini tab data, right? It says the predictor, so it'll be a table essentially. Here, the rows will be given your constant and then whatever your X is. So in this case, this is referring to the miles driven plot from the other day. And then it'll give you your coefficient and then your standard error for your coefficient and then a T and a P. These over here are not to be worried about until we get very much further into the year. So do not stress about what's going on over here. The things you need to focus on are this, 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 and this. So here, where it says constant, the first number next to it is y-intercept. Where it says miles driven, or whatever your x was, the value next to that, that is the slope. That tells you the slope for x versus y, right? It tells you this is the number that you're multiplying by your x, right? So there you go, that's your slope. So there's your A, there's your B. Over here, they have the standard deviation for the residuals. That is that S that we talked about. And then here they have your R squared. Sometimes they'll include the R, sometimes they'll give you R squared as a decimal, but it'll say R hyphen SQ equals a number. That is your R squared. So the way we would look at this data, we could answer several questions. First of all, we could give the equation for the line, y hat equals 38,257 plus, or was it plus or minus? I feel like it was minus, but it didn't put the negative sign there. I think that's a typo. So we'll just go with the data that we're given, plus 0.16292x, right? And if there's a minus sign there, then we make sure we include that negative sign. So there we have the equation for the line, and we can answer the slope and y-intercept questions as well. For the standard deviation question, we can use this value and plug it into our answer. So 5740, we go up. So when using the least squared regression line with x equals miles driven and y equals price, we will usually be off by about usually be off by about $5,740. For the equation, it says interpret the R squared value. About 66.4% of the variation in price can be accounted for by miles driven. That would be how you answer that. Done and done. So a lot of questions can be answered from this data if you know how to read it. Again, we aren't usually going to be calculating the least squared regression line by hand, but if you are, this is how you come up with the slope and the y-intercept. First of all, please note that the y-intercept actually has the value for the slope in it, so you need to calculate the slope first. The slope is found by r times the standard deviation for y divided by the standard deviation for x. So a lot of work goes into that. At least use the calculator to find standard deviation for y and x and then multiply it by r. That gives you your slope. For the y-intercept, you take your mean for your y minus the slope times your mean for the x. So you have to have one variable statistics for y, one variable statistics for x, and you have to find r. If you're using a calculator to find r, you might as well find the least squared regression line by hand, in my opinion. But that's just me. If you don't have a calculator that can do that, but for some reason can find r, this is how you would do that. And lastly, brief conversation about outliers and influential observations. So notice that because r is in the calculation for slope, r is also in the calculation for the y-intercept. So essentially both the slope and the y-intercept have r involved in their actual calculations. So outliers in either direction, because r is affected by how spread out everything is, outliers decrease r. Therefore, outliers are going to have a big impact on everything about our least squared regression line. So we also need to know the difference between an outlier and an influential observation, right? An outlier is an observation that lies outside the overall pattern. Usually they are outliers in the y direction, but not in the x direction, and they have large residuals. All right. An observation is considered influential for a calculation if removing it changes the results for the calculation. So usually when we're referring to an influential point, we're talking about a point that is far away from the rest of the data in the x direction, right? So you can imagine a point being an outlier in the x direction can change the slope dramatically. I showed you example the other day on the other video how moving the point up and down greatly affected the residuals and shifted the line up and down. However, moving the point left and right and making an outlier in that direction greatly affected the slope and changed everything about the line. So having one point far away from the rest of the points is going to have in the x direction is going to be very influential on the rest of our data. So that's why you refer to it as an influential point or an influential observation. And that's it. I hope this was helpful.